All right, I've got 11 o'clock, so I'm going to start. You do have a quiz, a take-home quiz that I asked to have done today, so please turn that in. And the bonus, I asked for it to be separate, so if you do have it separate, just put it on the side, just like that. Now, on these take-homes, they are due, of course, today, right? Like this one, it said it's due today. What I mean by that is it's due right now, like 11 o'clock, not at 11:10, not at 11:05, not at 11:30, right? So people who come in 30 minutes late, 20 minutes late, 10 minutes late, they'll get points taken off this time. Next time, I won't accept it. All right, that's just because it's only fair that you turn it in right now. Someone shouldn't be out in the hallway working on it for 30 minutes, get that advantage over you, right? So that's being recorded and documented. Beginning of class is when it's expected. All right, anyone else? I also have quizzes for you to pick up. So what I'll do, so I'll just call your name, come grab them. See, Joshua, Diego, Adrian, Tamara, Thomas, Allie, Raul, and we talked about that, right, Allie? Yeah. Okay. Jose. Oh, whose folder? Is this, sir? It's yours? No, it's all right. I don't want you to lose it. Let's see, Mark, Joshua, Jose. Sorry, other one. And Dan. Yep. That's all I've got right there. So adding on to what I just said about turning in your quizzes on time, if something happens where, you know, you get, is that bonus? Bonus piles right there. If something happens, you get stuck in traffic or something like that, and you know you're going to be late, and you don't want me to take a 0 on that for you, pull over on the side of the road, take a couple of pictures on your phone of your work so that you have it documented that at the time I wanted it, it was done. Then we can work something out, all right? That doesn't mean, oh, you know, just don't come to class and take pictures and scan them. I mean, I expect it to be turned in. All right, we are going to start class with any questions over any homework or any questions at all over the quiz. I normally do not post the answers to these quizzes. I encourage you to come into my office if you have questions after I grade them and hand them back to come back and talk to me, and you know, I'll address any questions that you have over that. So no questions on homework? Yes? Were you asking like specific questions, or were you offering to go through whatever. What's your question? Do you want to know how it was worked out, or you want to know what the answers were? Okay, so the dot product, ooh, I don't know about that. Did you get to an equation? You did? Let me. Yeah, it's Dan, right? So you had a 4th degree polynomial. You know, I think I have my answers here. Let me bring it up because I believe I have it here. See if I can find it. All right, this was it. Can everyone see that, or do you want me to kill some more lights? Kill a couple? There we go. So you start out, you dot the two vectors together, which means you just multiply the components and add them up. And when you do that, you should have got that fourth degree polynomial, b to the fourth minus 4b cubed minus 19b squared plus 46b plus 120 equals 0. And then you look at all the factors of the number 120. You list out all possible factors. Those are all the numbers that multiply in, or divide into 120 evenly. Then you begin synthetic division on these. And you do synthetic division until you get zeros as remainders. And the first time it happened was at -2, which means that -2 is a solution. And you can continue to do that, or you can use this synthetic division to actually factor the original polynomial, and then try and solve this one, do synthetic again, and get a remainder of 0, and that means -3 is a solution. And then use it to factor again. So if you haven't done this, I'd be happy to walk you through like what's happening here. But you should get 4 answers, 4 solutions: -2, -3, 4, and 5. If you just came in, turn in your stuff, and next time it needs to be on time. Is that enough, or, I mean, sure? Okay. The multiplication part, maybe? There was an issue up here? Okay. Right in here? Yeah, this right here, when you multiply these two, you should get 120. Then the middle terms cancel, and then you should just get 19b squared.
Isn't there a way, and I mean, I can honestly understand why you want to do like a long version of that. Isn't there a shorter way to do it?
Like how?
I don't know. I could have sworn I learned something from Calc 2 where they taught us that, yeah, well, it's just pretty much synthetic division all around with all those factors. Just try one for each one and see if it works.
Well, that's pretty much what I did, except that I used the synthetic division to factor further. You could just keep trying until you get zeros. Well, I mean, I'm just saying there. You could have just taken. You're saying still use that list of numbers.
Well, like instead of just doing that list, like you have that whole equation
Mm-hmm.
equal to 0. Wasn't there another way to do that by doing synthetic division and getting all the factors?
Well, there's different ways of factoring polynomials or breaking them down, but that one will only go down with the synthetic. As far as I've tried, that's the only way it'll go.
Right.
Yeah. Of course, you could type it into a computer. You could graph it and find the x-intercepts, but that kind of defeats the purpose. Was there a question, Thomas? No? Okay. All right, we're going to pick up where we left off. We have a lot to do today. We had started talking about the dot product last class, properties of dot product. We showed how we could use the dot product to verify whether a triangle was a right triangle. So one of the main results from last time was that two vectors are perpendicular if and only if what? Dot product is 0, right? Okay, now we are going to talk about what's called vector projections. I'm going to give you this example here in 2-dimensional space, but it extends out into 3-dimensional space, just easier to visualize. So given two vectors, we can project one vector onto the other. It's like casting a shadow onto the other one. That shadow will create a new vector. So let's take a look. I have two vectors here. I can drag them around. You go to the other one. And it's kind of hard to pick this up, but do you all see this purple vector right here? Looks black. That is the projection of the blue one onto the red one. So have you ever heard the term dropping a perpendicular? To drop a perpendicular? Just imagine you kind of rotate your head so that this perpendicular is up and down, straight up and down. So what you're doing is just dropping from the tip of this straight down onto this red one where it hits at a perpendicular at a 90-degree angle. Where it hits is going to become the tip of the new vector, and then the tail is the same as the red. So that vector there is the projection of the blue one onto the red one. Now we could go the other way around. I'll move this red one. I could project the red one onto the blue one. So what I'm doing is I'm coming in here, I'm looking at a perpendicular line, I'm looking at where it would go and touch the red one. So dropping the red one onto the blue instead looks like this. Do y'all see that? So given two vectors, you can project one onto the other, or the other way around. Now what happens if I take this red vector, make it shorter? It's going to shorten the length of the projection, right? What happens if I take this red vector and I go past the blue one there? Well, then my vector projection is still a vector. Notice it's parallel to the blue one, but it's actually longer than the blue one. So you can have a projection of a vector onto another one that creates a vector that goes past the other vector. Does that make sense? Yes? Now what happens if I take this vector and I bring it out 90 degrees? The projection would be what? The zero vector, right? What if I go down with this red one? The projection is going to run parallel to that blue one, right? But it will be pointed in the opposite direction. So projecting this red vector onto the blue one here, your vector is pointed in the opposite direction of the blue one. So as long as the two vectors are not exactly the same, or they're non-zero vectors, the projection makes perfect sense. You can imagine projecting any vector onto the other. Yes? Now, there are two formulas that we're going to look at now, right? If I'm going to project this red vector onto the blue one, it creates a new vector. I'd like to know how I can come up with that vector, right? Like, what is it? So someone gives me two vectors, I project one onto the other. What's that new vector? What's that vector projection? So here's the formula. Given two vectors u and v, the vector which is the projection of u onto v, right? We could do it the other way around, v onto u, but the one that's the u onto the v is called the vector projection of u onto v. The notation we use for it is PROJ, subscript the vector v, and then u. So u gets projected onto v. So I just remember it like the one that's subscripted is the one that's getting projected onto, all right? Here's the formula that we use to determine what this new vector is. The projection of u onto v is v dot u over the magnitude of v squared times v. And what I point out here in the note is that v dot u, right, when you dot two vectors, what do you get? What comes out when you dot two vectors? A number, right? So this numerator is a number, right? The magnitude of v is its length. So that's a number, and you square it, that's still a number. So this whole thing in here is just a number. That number is sitting in front of v, which means that our projection is a scalar multiple of v, which makes sense, right? If I'm projecting, let's say this red one is u, if I'm projecting u onto v, then this purple one should be some scalar multiple of v. And the scalar multiple is just this piece right here in front. Now sometimes we are not interested in actually finding the vector itself. We're interested in just finding its length. So back here, this formula gives us the actual vector, right? That's a scalar multiple of v, so the answer would be angled brackets and then some vector. But we might be just wanting to know, instead of the vector, just how long it is, right? Its length. So we could just take the magnitude of this, couldn't we? And that would give us the length. But that formula is a little bit harder to work with. So we have an easier formula, and we have some different language we use. We call it the scalar projection. Instead of the vector projection, we call it the scalar projection of u onto v. And all it is the length of the vector projection. The notation we use is comp, and then subscript v and u. And the actual comp comes from the word component. So this is the component of u onto v, or the scalar projection. And there's the formula for it. So this formula is very similar to the previous one, right? V dot u is exactly the same, but instead of magnitude of v squared, it's just magnitude of v, right? And then that whole vector v is gone. And this is just a number, and that's how long the vector is. Is that okay? Yes?
So, the one before, that wasn't the length of the projection vector? What was that?
This right here is the vector itself. Right? Remember, a vector has components, right? You have an angled bracket, and you've got numbers in there. That's a vector. Its length is its magnitude. That's a different thing. That's the square root of the sum of the components squared. That's how long that vector is. So this formula actually gives you the vector itself. The other formula gives you how long that vector is. Is that answering your question? No? Okay.
That formula comes up to a number.
No, this part in front, right here. This part right here is a number times v. Remember, any scalar number, right? This number, this is a scalar times v. So any scalar times v is a multiple. Yes, yes. The unit vector in there, right here. Well, you have to kind of look at this with like order of operations, because you can't split the v over its magnitude, because that's not our true product the way we've looked at products in the past. That's the dot product. Does that make sense? So there's no cancellation there. Good question, though. Okay, so now note the values of the projection. So what I did here in this one is to kind of show you, like, answer your question. We have two formulas. We have the PROJ formula, and we have the comp formula. If I compute the projection formula, right now I'm doing the blue one onto the red one, right? If I do my projection of the blue onto the red, I get a vector. Now, Mathematica can't do, it's easier for me to do the braces instead of the angle brackets, but this is a vector, okay? So imagine that those are angle brackets. This is my projection. It is a vector. Now, this is its length. Now, notice it's negative. Why do you think it's negative here? It's the opposite direction of red. That's right. So anytime you take the scalar projection, if you get a negative, what you need to keep in mind is that it's pointed in the opposite direction of the vector you're projecting onto. Now, if I move the blue one over to the other side, my scalar projection will be positive.
But that still doesn't change the fact that if you get the magnitude involved, you won't have the negative, right?
Pardon?
Like, you just got the magnitude of the projection vector? It wouldn't be a negative.
That's right, it wouldn't. But this component here, see, your dot products can be negative, right? Your dot product can be negative. Dot products are negative whenever your angle is greater than 90. So the component can give you a little more information than just having taken the magnitude over outright. That's right. It shows you the direction. That formula actually shows you which way it's pointed relative to the one you're projecting onto. Okay. Any questions on the difference between those two? This can become useful later. Very useful. So let's do one of these here. Let's do this one. I'm going to do example 10. I'll let you do example 9 on your own. Only reason I'm doing example 10 is to make sure that when you read these things, you're paying attention to where the variables are positioned. If you're being asked to find the projection, what is this? Projection of what? V onto U, right? That's your projection of V onto U. So my formula is going to change a little bit, right? Because the formula that I have, that I gave you, is the formula for the projection of U onto V, right? U onto V. So if we're going to do V onto U, we're going to have to switch everything here, right? This is going to be U dot V over U magnitude of U squared, and then U will be there, right? So everything gets switched. That's the only reason I'm doing example 10, just to show you that changing what's being projected is going to change the way you use the formula. So I'm going to do what here? I'll write down the new formula. U dot V over magnitude of U squared times U. Everyone agree? That's the formula converted over? Let's not confuse this dot right here is a dot product. This right here is just scalar multiplication. So let's go ahead and get these pieces over here. What is U dot V? -6 plus 28, right? Which is 22, right? What else are we going to need? Magnitude of U, which is going to be the square root of 4 plus 16, so root 20. And now I can plug everything into this formula. U dot V on top is 22. The bottom is the square root of 20, but then what? Squared, and then times what's U? The vector 2, 4. What's 22 over 20? 11 tenths. And then we're going to scale that through here. So you should get the vector, right? The vector 22 over 10, 44 over 10. So if you project the vector the vector -3, 7 onto the vector 2, 4, we should get that result. Now, I also ask in this problem for you to find the component of V onto U. So let's do that now. What would the component of V onto U be? We already did most of the groundwork for this, right? It's U dot V over what? Magnitude of U, right? And we already have all this. This is 22 over square root of 20. Is that all right? That's fine. But I was going to ask for someone to do it on their calculator to give us a decimal approximation. Yeah, I mean, for that, I always like to see the exact answer, which is this, and then the approximate after it. You know, just approximately equal to, what do you got? 4.919. Okay, sounds good. Approximately 4.92. Now, I've also asked you to sketch things. So I think I will do that. So first, I'll go to 2D. And I have two vectors. One of them is the vector 2, 4, so that means I go out to the right 2 and up 4. Create this vector. This is my vector U. My vector V is the vector -3, 7, so -3 is to the left 3, up 7, which is here. I have this vector, It's my V. If I project my V onto my U, which is what I was doing, right? V onto U. Kind of hard to see here where it's going to hit, but what was our answer? Our projection vector was 22 over 10, which is what? 2.2, 44 over 10, 4.4. So if I go out to the right 2.2, that puts me about right here. And I go up 4.4, 1, 2, 3, 4.4, somewhere around here. So I'm looking at a vector. This vector, I'll do it kind of dash through here. It goes up to here. And if I drop a perpendicular down like this, you can kind of, do you agree it looks right? I mean, that looks okay to you? That looks like the projection of V onto U.
So the comp is the same scalar without the square, or without
The comp is the same as the projection without the bottom being squared and without the vector V in this case, yes. So it's the scalar multiple that we had from projection, but not squared on the bottom. All right, that's it. To my picture. Okay, so the projection, I just took this projection vector, right, 2.2, 4.4. I went out 2.2, I went up 4.4, and then I drew a vector from the origin out to that, to this point. And then it looks like if I dropped a perpendicular down, that is where it would be. Okay, here's the way it works with projection. If I'm going to project the V onto the U, what I need to do is imagine moving a line across U where it's always perpendicular, okay? And then move it until I get and touch the tip of V. And when I do that, it's not a perfect drawing, but when I do that, I get here, and this is where it is. It's right there. So it's like dropping, we call this dropping a perpendicular. You drop a line perpendicular down to the red one. That is the tip of your projection vector. Okay. Let me move back to this picture here. If I move along my red, I'm projecting blue onto V, right? Or blue onto red. If I move with the perpendicular, I'm always perpendicular to the red. When I touch the tip of this blue one, drop it, that is my projection vector.
Oh, okay.
You sure?
So whatever's projecting onto the other is connected to where it makes a 90-degree angle.
Yes. It might be easier if you looked at everything flattened out. Like if this were the vector V, and I had some vector blue here like this, and I just said drop a line straight down, right? This would be your projection vector. The problem is that we're slanted, okay? We're turned. So just turn your head and drop straight down. That's what we're doing.
So it can be, sometimes the projection vector can be
shorter or longer, yes. In this case, it's a little longer, right? A little longer?
So what's the purpose of the projection?
We're going to see that in the next section. Oh, not the next section, the one after that. This is what we're going to use to be able to take, I don't want to get the carriage in front of the horse, but imagine that I have a plane in three-dimensional space here, right? Extends in each direction forever, just sitting out here. I have the projector up there. I want to find the shortest distance from this plane to that projector. There's some point on here, right, that's closest to that projector. The way we're going to find that is using projections. So we're not using it yet, we just need to understand what it is. Yep. All right, so example 11. Here's a vector U. Find a vector V such that the component of U onto V is 3. such that the component of u onto v is 3. So all I give you is that u is the vector 4, 0, negative 1. And I give you that the component of u onto v is 3. Ask you to find what v is. So the only thing we really have to work with here is, what is the component of u onto v? What is that right there? What's its definition? So it's v dot u over magnitude of v. We know that has to be 3. Yes? What we do know in this problem is what u is, right? So how can we do this? Okay, so just call v v1, v2, v3. Is that okay? If I do that and I rewrite this, it would become v1, v2, v3 dotted with 4, 0, negative 1 all over, what's the magnitude of v? Square root of v1 squared plus v2 squared plus v3 squared. That must all be equal to 3, right? Now when I dot the top through, what do I get? 4v1. I'll continue it up here on the top left. I get 4v1, 0, and then what? Minus v3 all over that denominator equals 3. So how about this? Instead of putting it all over that denominator equals 3, why don't I multiply both sides by that denominator? Everyone okay with what I just did? I brought this right here, multiply on both sides. I'm trying to solve this equation, right? The issue that I have here is I have one equation, right? I have 3 variables. You're never going to have a unique solution whenever you have one equation and 3 variables. So this problem is asking for you to find v. It doesn't say that it's unique. So that means we can find any v. It doesn't matter what it is. Just find one that satisfies this. May not be the only one, but just find one. So what I'm going to do to solve this is just try and pick some values to make things a little easier. How about this? How about I'm going to just let v3 be equal to 0. And maybe that'll help me go grab a v1 and a v2. I don't know if it's going to work, but let me try it. If v3 is 0, then I get 4v1 equals 3 times the square root of v1 squared plus v2 squared, yes? Can I let v2 be 0? If v2 is 0, this equation may not have a solution. The only solution may be 0, 0, 0, which wouldn't work because that's the 0 vector. Guess what I'm getting at is I chose v3 to be 0 just to try and make it easier. I'm trying to say, okay, look, the v can be a lot of different things. Let me just let the third component be 0 and see if I can get the other 2. But maybe by trying to let v2 be 0 is too much. That no vector that has that form will work. So instead, why don't I just try and square both sides to get rid of that root? Okay. 16 v1 squared equals 9 v1 squared plus 9v2 squared. Right, I squared the 3, I squared the square root went away, I distributed the 9 through. Now, don't I have v1 squared on both sides? So subtract 9 on both sides and you'll get 7v1 squareds, 9v2 squareds. Let me do division by 7. How about taking a square root on both sides? Now I should have plus or minus, right? When I do square root. But I'm only trying to find one possible answer. I don't have to find a bunch of them, so why don't I just do the positive case? Do y'all agree with that? So what do you say we let V2 be 1? Then we'll know a V1, won't we? So let's let V2 be 1. And that means that V1 must be 3 over root 7. So what's the vector that I think is going to work? 3 over root 7, 1 and 0. How could I check that? I could actually do the component of it and see if it's 3, right? Do y'all want to check it or not? No. It would come out pretty clean, I think. Because look, what's u dot v? 12 over root 7, right? So I'd have 12 over root 7 over, now what's the magnitude of v? Right, that's what this is. So what's the magnitude of v? It's this squared, right, which is 9/7 plus this squared, which is 1, all under square root. What's 9/7 plus this right here? 16/7. So 12 over root 7 over root 16/7 is what? 4 over root 7? And if you flip it and divide, you get 3. So I've just shown a solution, that's all. The purpose of this problem is just to, show you how you can work with these vectors and use the formula to try and extrapolate some answer from it. Well, with partial fraction, we usually had multiple equations, right? So we usually had unique solutions. There was only one way to decompose something. Here, we're coming up with equations, but they're so arbitrary, we could have many different values. This is not the only vector v that would work. So I guess that would be the difference. I just found one, yeah. Sure. Yeah, if you wanted to, you could just make sure it worked. I chose v to be 0, v3 to be 0 up here, didn't I? I could have said let v1 be 0. Well, no, I couldn't. Why couldn't I let v1 be 0? Why not? Why not? Or could I? Okay, if v1 is 0, right? The only thing you have to be careful with is if v1 is 0, what can you tell me v3 cannot be? Negative. Or no, it would have to be negative, sorry. Because look, if this is 0 and this is 0, the right side of this equation has to be a positive number. And this is negative v3, so you couldn't have v3 be positive because then you would have a negative equals a positive, and that's not going to happen. So the reason I chose v3 to be 0 is that I just recognized real quick that if that's 0 and that's 0, I shouldn't have any problems with signs. But that's a subtle thing. I mean, the point of me saying that was just that I chose V3 to be 0. You could have chosen V2 to be 0 and still gone through this problem the same way.
Right. You said that V3 couldn't be negative?
If you let V1 be 0, then V3 couldn't be positive. That's what I was saying. If V1 is 0, V3 has to be negative for this to work. Because a negative in it minus a negative would be plus. Right?
Yeah, but if you work it out and you square both sides, wouldn't that be a positive anyway?
Well, but that what happens when you square both sides of an equation is you introduce the possibility of what are called extraneous solutions, right? So anytime we've done anything algebraically and we've said, okay, I'm going to square both sides of the equation, we get solutions. Those are potential solutions, but they aren't guaranteed to be solutions. I mean, the simplest example is this. What if I tell everyone in the room right now x is -4, okay? I'm defining x to be -4, right? And then you come in here and you square both sides of this equation, right? And now I say, okay, I told everyone what x was, right? But then we do squaring on both sides, and then some student walks in, I say x squared is 16. And they go back and they take the square root, and they get x is plus or minus 4, right? Well, it's not plus 4, it's minus 4. I said it was minus 4. So by squaring both sides, you get a list of potential answers, but not all of them necessarily work. That's a generic example, but it applies on the big picture that squaring both sides of an equation is a totally legitimate operation algebraically. But you have to know that you may have screwed up some of the answers. Like, some of them may not work. That's why you have to check them. Okay, let's proceed. I think we're done with that section. That's the homework. The only difference is that's page 556. That's page 556. Now, when we started, we said that there were two major operations with vectors, right? Well, we had scale. We could add two vectors, subtract them. We could scale them. Then we introduced this whole thing called dot product. There's another multiplication between two vectors, which we call the cross product. So before I begin, we want to remember that when you write the vector u in two-dimensional space, u1, u2, it can also be written u1 I hat plus u2 j hat. That was that other notation. I hat and j hat are the what? What are those? Call them the standard basis vectors. Here in 3D, we have I hat, j hat, k hat. Those are our standard basis vectors. That's just notation. We said that when we had the dot product, right? When we took the dot product of two vectors, we got a number, didn't we? This cross product that we're about to define is only defined in three-dimensional space. So if you have two vectors in three-dimensional space, the cross product is well defined. If you have two vectors in two-dimensional space, the cross product is not defined. So we have a way around it, okay? We do have a way around that, but we'll just save it. You just extend the two-dimensional vectors into 3D. But the operation itself requires two vectors from three-dimensional space to be able to work it out. So if someone gives you two vectors, u and v, in three-dimensional space, here's the definition of the cross product, which you can memorize this formula if you'd like. I'm not going to encourage you to memorize the formula. Where do I put it here? Okay, I kind of skipped this part right here. I want to make sure I point that out. This cross product takes two vectors, and when you do a cross product, it spits out a new vector. Right? Dot product spit out a number. Cross product spits out a new vector. That's a very, very important detail difference between dot and cross. All right, so let me show you a couple of ways to do cross products by hand. I will expect everyone to be able to do a cross product by hand. How many of you have done cross products before? Okay. There's several ways of doing it. I'm going to show you the way that most of my students have told me they like to be presented, you know, this version of it. So I first have to see if any of you recall something from college algebra called a determinant. Of a 2 by 2 matrix. If somebody gives you a matrix A, B, C, D, the determinant, we see DET, the determinant of that matrix is A times D minus B times C. So it's this A times the D minus the B times the C. Anybody? How many of you have seen that before? Okay. If you can remember what a determinant of a 2 by 2 matrix is, it'll make doing cross products a lot easier. All right? So I want to start by doing a cross product by hand, and then we'll talk about what it means and, you know, what it actually represents geometrically. But we first have to be able to do it by hand. All right, so I'm doing example 1. I have two vectors. U is the vector 2, negative 3, 5. V is the vector 4, negative 1, 3. All right, so this is the way, like I said, that most students have said they like to do it. First, they write down I hat, J hat, K hat. And then below this, they write down the components of the vectors. So I'm going to start with U. I'm going to put 2, negative 3, 5. And then below 4, negative 1, 3. When I do a cross product, right? When I do a cross product, it's going to spit a vector out, right? It's going to spit a vector out. That vector that comes out should have an I, a J, and a K, right? An I component, J component, J and a K component. So how do we determine each one? Well, here's how it's done. First thing we do is let's say we want to do the I, right? Let's figure out what the I is going to be for my cross product. I come over here to I, and this is very hard to do with the way the board is, with the way I'm doing this class, but I'm going to actually cover that up. So I'm going to put my finger over this, my hand over that on your piece of paper, and I'm going to see a 2 by 2 matrix there, right? See that little 2 by 2? I'm going to calculate the determinant of that 2 by 2. So what's the determinant of this 2 by 2 matrix? Negative 3 times 3 is negative 9, right? Then minus 5 times negative 1. So I'm gonna just write that down below here, like where I got this. I did negative 3 times 3 minus 5 times negative 1, and that gave me what? 9 plus 5 is negative 4. That okay? Any questions? If you want to know what the I is for your answer, you cover up the I and you do the determinant on the 4 numbers that are there. What do you think you do to get the J? To get the J, I cover up the J. We're not here to explain why this works. If you match it to the formula, it is exactly this. This is just a way that students have come up with a way of doing it really quick. You'll get fast at this eventually, all right? You cover up J, and now you do the determinant of that, which would be what? 2 times the 3, right? Minus the 5 times 4. However, there's a little bit of a hang up here for the J component. Whatever you get for your J, you have to change the sign of the answer. Only for the j you have to worry about this. All right, so I'm going to do the computation. Give myself a little room here. I'm doing the 5, sorry, I covered it up. It's the 2 times the 3 minus the 5 times the 4, which gave me 6 take away 20, right? Which was what? Negative 14. However, because I'm on the j component, I come in here and change the sign. So instead of negative 14, I get positive 14. I'll box these answers I'm getting here. Now for the k component, what are you going to do? Cover up k, right? And then do the determinant on the other two. So I'll cover up this, and I'll do the determinant on that, those 4 numbers. And I don't have to change the sign on this one. So it'll be negative 2, take away what? Negative 12. So it'll be negative 2 plus 12, right? Which is 10. I'm not going to show that one. This is 10. Just remember, always change sign, right? Don't forget that on the j component, always change that sign. So our answer I'm going to write down here is u. Now the notation we use is cross v. Okay, that's not that old school multiplication symbol you learned in like 3rd, 4th, 5th grade, right? This is the cross product now. The cross product of these two vectors is the vector negative 4, 14, 10. A lot of your calculators can do cross products. I would encourage you to learn how to do a cross product on your calculator, because when we get to the midterm, right, we just have midterm and final in here. When we get to the midterm, if you have to compute a product, a cross product, I would not want you to get slowed down by this. So if you don't know if your calculator has cross product, just come see me, because if it doesn't, and if it's a Texas Instrument calculator, we can just write a program for it real quick. It'll be simple and takes a couple of minutes and we're done. But you have to come see me if you want to do that, all right? If you have a TI-86 or up, it has cross product on it. I don't know if the 84s or 84 plus do, I forget, but I know for sure the 86, 89, they all have cross product. Any questions on that? Okay, you can ignore this right here because when I made these notes, I was showing my students a different way of doing cross products. And after going through the different methods, the one I showed you is the one that students mostly preferred. So this is just another way of doing it, which I'm not showing you. Now, what is the major result here? What's the importance of the cross product? We already know that the cross product gives you a new vector. What makes the vector so special is that it is always orthogonal to both of the vectors it came from. Always. We often use cross products when we are trying to find a vector that is perpendicular to two other vectors. So let me try and explain this in the classroom with my markers. Look, if I have if I have two vectors in 3-dimensional space here, I can take them and attach them tail to tail, right? Yes? Now, these two vectors, if I kind of tilt it, you can kind of see that there's like a plane that this creates, right? If you take the cross product of these two vectors, the vector that you get out will have to be orthogonal to the first one, and it will have to be orthogonal to the other one also, which means that it looks like this. So it's almost like a right-hand rule. It's almost like your thumb coming out perpendicular to both. And it'll always be that way, always. So if I take the ruler and call that U, and I take the markers and call that V, If I do U crossed with V, my fingers go from U to V, crossed to V, the cross product vector will come out as my thumb following the right hand rule. If I were to do it the other way and go and cross V with U, I turn my hand over and I curl from V to U and the cross product comes out the other side. They're the same, the vector that comes out either way have the same length. They're just pointed in the opposite direction. Understand? So I would like us to take the vectors that we just took those vectors, right? Those were the ones we had, U and V, and we crossed them. I want us to show, all right, that the cross product is orthogonal to both. So I said it is, right? I said it is, but now I'd like us to just convince ourselves that it worked for what we just did. So how would I do this? I want to show that the vector I just got, which was what? What was our cross product? Negative 4, 14, 10. I want to show that that's orthogonal. So another way of saying that is to draw like a little upside down T. Show that that vector is orthogonal to what? U and V. So let me start with U. 2, negative 3, 5. And then after that, I want to show that that same vector is orthogonal to the V, which was 4, negative 1, 3. How are you going to do that? That's right. Two vectors are orthogonal to each other if what? The dot product is 0. So just real quick, do a dot product on these. Dot product, this times this, it's what? Negative 8. This times this, negative 42. And then this times this is plus 50. And your answer is 0. So they dot to be 0, don't they? Those two vectors dot to be 0, which means they're orthogonal. And then, if I do the same thing here, get negative 16, negative 14, positive 30 equals 0. So it checks out. That's bad notation. I'm just kind of showing you the ideas, right? I'm not actually writing it out explicitly. So are you convinced? Curious well, I'm wondering if just because this worked this time, does that mean it is going to work all the time? You know, like how would we show that this works all the time? What would be the only way to do it? You would have to do it arbitrarily, right? So let me show you how you would do that, just to kind of show you the way that math people think. All right. This is the definition of U cross V. All right, I said don't memorize this formula because we'll do it with determinants, but this is the formula right here. So what I'm going to do is I'm going to take that and I'm going to dot it with U. So I should be able to draw right on this here. I'm going to dot that with U. That's U1, U2, U3, right? If things are what I said they were, that should become what? 0, right? Okay, let me try and dot this. What happens if I take this and multiply it times that? I get U1, U2, V3 minus U1, U3, V2, correct? Then I take this, multiply it times this, I get plus U2, U3, V1 minus U1, U2, V3, right? Then I do this one here. That's plus U1, U3, V3 minus U1, V2, thank you, V2, U1, should I lost my spot? No. U3, so U2, U3, V1. Does everything cancel? U1, U2, V3. See U2, U3, V1, and U1, U3, V2. They all cancel. Everything cancels out. You get 0. And then you could show the same thing for V1, V2, V3, and that would show in general that this always works. That was just a little exercise. That's not that important. All right, so here's a picture. It's kind of hard to see this, but that was what I was trying to show you in class. If you have the ruler is the red one, and then the markers were the blue one, then the cross product will always be this black vector that's orthogonal to both. Kind of hard to see in 3D, but that's what's happening. All right, show that U cross U is 0 for any vector in R3. If you cross a vector with itself, you get 0. How would I show that? Well, I take U, I call it what? U1, U2, U3? I want to cross it with itself. So to do a cross product, I write I, J, K. Underneath it, I write U1, U2, U3. What am I crossing it with? U1, U2, U3. And now you do your determinant thing, right? So I'm going to get 3 things out, I hat, J hat, K hat over here. To get the I, cover up I here. What would I get if I do the determinant there? U2, U3 minus U3, U2, or U2, U3 again, right? And that's just 0. And then when you do the J, you'll get what? U1, U3 minus U3, U1, which is 0, change the sign, still 0, so 0, right? Do I need to go through the rest? No. Okay, so you get 0, 0, 0, which is the 0 vector. Did I put that in my notes? Was it 0 vector? No, that's not. That's a vector. Make sure you put that as a vector. Oh. It won't let me do what I want to do here because that program is running. There. That's the 0 vector, right? What's that? Yeah. Well. What? Say again? To both those vectors, right? Correct. Now, yes, but usually when we define orthogonal, we say 2 non-zero vectors are orthogonal, so we assume they're non-zero, but technically, yes, the 0 vector is orthogonal to both. Because think about it, the 0 vector is 0, 0, 0, right? You dot that with anything, you get 0, 0, 0. So it is orthogonal to everything. But there's another thing that we need to look at here that might be possible. If I have the same vector, right, and I cross them, I got 0. What if I have 2 vectors that are just parallel? They're scalar multiples of one another, right? What do you think their cross product is? Well, we'll do that in a second. This right here is something that you're going to need to be able to do. So this is like one of those things you draw a little star next to, because it's one of those fundamental things that when you're doing your homework and you get to this problem and I'm like, well, you've got to find a vector that's perpendicular to the plane. You're like, well, I don't know how to do that. And I'll say, okay, well, wait, what about example 4? We did something like that. Okay, so this is a good skill we're going to use over and over in this class. Find a vector which is perpendicular to the plane that passes through these 3 points. So what we're doing here is we're saying that we have in three-dimensional space 3 points, right? I'm only drawing the lines connecting these to help us see that that's three-dimensional, all right? I'm not saying it's a triangle. I'm saying we have 3 points in 3D space. I would like for us to find a vector which is perpendicular to this plane that's created by these 3 points. So now we've got the 3 points, we've got the plane. I want us to find a vector that's going to be perpendicular to the plane, like that. How can we find a vector perpendicular to that plane? Okay, make 2 vectors out of the points, any 2 vectors, right? As long as they're not the same vector, not scalar multiple. So I can take this vector here, and then maybe this vector here, right? We'll call this one maybe U, and maybe call this one V here. And then what do you do with those 2 vectors? Take their cross product. That will generate that 3rd vector that will be perpendicular to both those vectors, therefore it will be perpendicular to the plane. So let me label these points 1, 4, 6. It doesn't matter how you label these, right? We're assuming we're in three-dimensional space, so we could rotate around, change our viewing point so that it would look like that. What's the vector U here then? -2 minus 1, so -3. 1, -7. You all agree? Okay, the vector V here, 0, -5, -5 again. Yes? Now what am I going to do? Cross product. Now, watch the way I'm going to do this, because this is something that you might start catching on to. Instead of rewriting everything and writing I hat, J hat, K hat, and then listing out the numbers, right? If you want to start getting quick with this, just put I hat, J hat, K hat up here. And you see what I've done is to get my first component of my cross product, I'm going to cover up I, and I'm going to do my determinant right here. So cover up I. What's my determinant there? -5, and then take away +35. So -5 take away 35. So -40. -40. Okay, now I do the next one. So I cover up the J. That's going to be what? -3 times -5 is 15. Take away what? 0. So I have -15, but with the J you always switch it. So 15. And then this last one here, cover up the K. 15. All right, -3 times -5, 15. Take away nothing, so 15. I think we already changed it, didn't we? Oh, we said negative, right? He's saying go back to J. That should be negative? We said negative, right? I just didn't write it down. Okay, look, J, I'll just run through it. I said negative, but I didn't write it down. -3 times -5 is 15. Take away nothing, that's 15. Change the sign, -15. So Yes, thank you for catching that. That is negative 15 right there, everyone. That's it. Yes.
So you don't really care which way the orthogonal vector goes?
Do not care. Do not care. Because if I wanted to, well, it's going to turn out that what we're going to do is we're going to use this normal vector for a lot of things. But see, I'm already calling it a normal vector. Sorry. We're going to use this cross product to define a lot of different things. And we won't care if it's pointed out one side of the plane or the other. We won't care. And we won't even care really about its length. Like we could scale it back if we wanted to. All we need is its direction. That's the main thing. And it could be a scalar multiple. All right? So if I multiply this thing by -1, change that to positive 40, positive 15, negative 15, all it would do was make the vector perpendicular come out the other side of the plane. That's all it would do. If I divide everything by 5, right, take everything divided by 5, I would just cut the length of it down. There are an infinite number of answers for this, for a vector perpendicular to the plane. So here's our theorem, our first theorem for the cross product. This may look familiar to something we had before. We had u dot v, right? Hold on. We had u dot v is equal to magnitude of u, magnitude of v, cosine of the angle between the vectors. By the way, just so everyone was clear on that, those vectors have to be attached tail to tail. That's the angle we're talking about. All right? Not tip to tail, tail to tail. This is very similar to that formula, right? Except instead of cosine, it's sine. And also, instead of just the cross product, it's actually the what? Magnitude of the cross product. Right? Because the cross product is a vector. The right side of this is what? A number, a number, and a number. So we can't possibly have the cross product be equal to a number. It has to be a vector. So that's why this formula, you have the absolute value there. Magnitude. The length of the cross product is going to be this. I won't go through this problem because I think we can do it in our heads. If we want to find the length of the cross, or the magnitude of the cross product, and we're given the length of each vector and the angle between them, it's just going to be what? 7 times 3 times sine of 31 degrees. And that's it. You just get your calculator out. So here's one of the results from that theorem. Two non-zero vectors, u and v, are parallel if and only if the cross product is 0. Very, very familiar with what dot product 0 meant the two vectors are what? Dot product is 0 meant two vectors are orthogonal. Cross product 0 means the two vectors are parallel. Why is that a result of this theorem? Yeah, if the angle between two vectors, if they're parallel, aren't they pointing in the same direction? So the angle between them is what? 0. Sine of 0 is 0. What if they're parallel but they're pointing in opposite directions? What's the angle between them? 180. What's sine of 180? 0. So either way, your magnitude of your cross product is 0. If the magnitude of the cross product is 0, that means that the vector itself had to be the 0 vector. The only way the length of a vector can be 0 is if it was the 0 vector. Hope that makes sense. So if that cross product is 0, and again, I don't have the correct notation on that, that's the 0 vector. then they're parallel.
Wait, and when you said, so that would be the same as the magnitude cross product of U and V, right?
Yes. Well, yes, that would, you could replace that theorem right there with magnitude cross product 0. Was there? No? I thought I saw something right there. All right, here's another result. Area of a parallelogram formed by two vectors. We'll give some actual meaning now to this magnitude of this cross product. If I take two vectors, remember, if I take two arbitrary vectors, there's u, and let's say I take some vector over here, v, I can attach them tip to tail. There's v, I've moved it over, right? Doesn't look like v, it looks like I changed it a little bit, but y'all with me? Okay. Now, we had talked about this whole parallelogram rule, that if you add the two vectors together, you create this parallelogram, yes? Well, it turns out that the area of that parallelogram is equal to the magnitude of the cross product of those two vectors. So you take this vector u, this vector v, you cross the two, you take the magnitude, and geometrically it represents the area of that parallelogram. Got it? This is that. This is the connection I'm making, trying to visualize. I have two vectors, u and v. I'm looking at the area of this little bluish purplish region right here. The area of that bluish purplish region is actually the length of this green vector, because that green vector is the cross product. Do you see the right-hand rule here? Right-hand rule, the green one is the cross product. If you measure the length of that vector, it's actually equivalent to the area of that parallelogram. So I'm skipping this example because all we have to do here is what? I mean, take the cross of those two. Didn't we do that already? So just take the magnitude of that answer. Square root of each of those components squared, add them up. That's the area. This problem is more applicable to what we're doing. Find the area of the triangle with these vertices. Are those the same numbers I gave you a second ago? Yes, right? Remember back here? Wasn't this our picture? I want to find the area of this triangle, right? Okay, so if I were to extend this out and create the parallelogram out of that, I can find the area of that parallelogram, right? By taking the magnitude of the cross product of two vectors. But that would give me the area of the whole parallelogram. I don't want that, do I? I want exactly half of it. So all I need to do to answer this question, most of the groundwork's been laid for this because we did all the stuff earlier. I just need to find that cross product, take its magnitude, and divide it by 2. Yes? Question? Okay.
So then, when you saw that cross product only divided two areas of parallelogram, nothing else?
That's right. But because the triangle is half of the parallelogram, I'm going to take half of it. So I'm going to go ahead and answer this question. The area of the triangle will be equal to half of the magnitude of the cross product of the vectors u and v. We defined those earlier, didn't we? We defined what u and v were off that picture. So I want half of the magnitude. Okay, someone help me out here. What were the components of that vector? 40 squared plus negative 15 squared plus 15 again? If we can compute that number, that's our area. I hope you can appreciate how powerful this formula is, because if you are trying to find the area of a triangle, normally you need like base and height, right? Or there were some weird formulas in pre-cal also, where if you had all the sides, you can come up with the area. Do you remember that formula? It was weird. It's like, what was that? Heron's formula, exactly. You don't remember ever seeing that? But all of those formulas were pretty much, you're in two-dimensional space. And even with Heron's formula, you needed all the sides, right? Here, just give me the three vertices of a triangle. That's all I need. In three-dimensional space, I don't care how it's oriented, right? Give me three vertices. I'll always be able to come up with two vectors. I'll always be able to cross them. I'll always be able to take its magnitude. I'll always be able to take half of that, and I'll always know the area. There's no trig involved here, right? No sine, no cosine, no tangent, nothing. Right? So that is a very, very useful formula. In fact, I believe, no, it wasn't on this. Oh, yeah. Surface area of the tetrahedron was a bonus problem, right? Anyone do that? No? Did you use this formula? No. Probably would have taken you about 10 minutes at the most with this formula. Okay, the problem on the take-home, which I offered as a bonus, so I'm not going to offer it again, is that you were asked to find the surface area of a tetrahedron. You know what? I have it worked out. Instead, why don't I bring it up so you can see without me having to write everything down. So what it was, ooh, man, this projector is really in bad shape. It's a tetrahedron. I gave you four vertices. All right, so what a tetrahedron, in this tetrahedron, imagine, remember the origin is that corner? Go out to the point 2, 0, 0, which would be, let's say, 1 table, 2 tables, okay, so over there on the ground. The other vertices, 0, 2, 0 is going to be 1, 2, so over here. So we got over there, over here on the ground, and then you have up 2, so up there, right? So imagine connecting that point down there, that point across, this point up, and then you got this plane coming this way, right? So that's what we're looking at right here. We're looking, kind of standing over right there, looking here. We've got that plane. Y'all see it? It's the corner. That's the corner of the wall, and then this is like this sheet coming up, and you got a triangle. I wanted the surface area of the entire tetrahedron, the entire thing. So let's start with this. That's what? What about this right here? This right here. That's this wall, right? What's the base of that triangle? 2. What's the height? 2. If you know the base and height of a triangle, you know its area, right? 1/2 base times height. So what's the area of that triangle? 2 times 2? 4. Half of that? 4 right? 2? 2. So the area of that one's 2. Okay? What's the area of this one right here? Same thing. What's the area of the ground part? That's this part down here. 2 also, right? Because it's 2 this way, 2 that way, diagonal. Okay, so we have that wall's 2, this wall's 2, the ground is 2. But what about the triangle going up at an angle? You don't know what the base is and the height, right? The height goes from this midpoint all the way up to that corner. You don't have that. You could get it. You could work all this geometry out and you could get it. Is that what you did? That's what you did, and I'm sure you got it. But the easiest way to do it is just create 2 vectors on that triangle. So I created the vector u, which goes from here, this corner, up to here. So I go from there to there, created a vector, and then create a vector that went across another edge of that surface, so from there to the ground here. That's 2 vectors, right, on that triangle. I know the area of that triangle then is half of the area of the parallelogram, so it's half of the magnitude of the cross product. So all I did here was Okay, that's a different picture, but there it is, half of the magnitude of the cross product. Here's my two vectors, here's their cross, here's their magnitude, here's half of it. Done. So I add that to 6, right? Because I had the 6 other parts, or the 2, 2, 2. So the answer would be 6 plus 2 root 3. Yeah, I did change the numbers on it. So it would have been a little more involved. It wasn't 2, 2, 2, right? Okay. You see how that works? Yes.
So you're assuming that the back end is 90 degrees and 90 degrees, and then you have more of a plane.
Where this back is 90 here and 90 here?
Yeah.
Well, I'm not assuming that. Because of the way that these ordered pairs are given, we're assuming this whole class that we're in Cartesian R3. Yes, so we are assuming that these axes are orthogonal to each other to begin with.
Okay.
Okay. Now, two vectors, they form a parallelogram. We can find the area of it. If you have three vectors, they form what's called a parallelepiped, which is like a three-dimensional shoebox that might be like leaned over. And here's an example right here. Can you all see that three-dimensional thing? It's called a parallelepiped. It doesn't have to be a shoebox, because shoebox, all the sides are perpendicular to each other, right? Like opposite sides are parallel, but they're all orthogonal. That's a shoebox. Parallelepiped does not have to be a shoebox. It can be kind of skewed over. Now, if all of the three vectors are orthogonal to each other, then it would be a box-looking thing, but this formula applies in a more general setting. So if you take three vectors, look at just the red one and the black one here. They form a parallelogram, don't they? And then this one up here is a parallelogram with the red and the blue. Yes? So when you take those parallelograms, put them together, you kind of get this three-dimensional solid. And the volume of that parallelepiped can be found using what's called the triple product. It's the cross product of any of the two vectors, crossing those, and then dotting that with the third vector, and then taking the magnitude of that. That's called the triple product, and it gives you the volume of the parallelepiped. Now, if you wanted to find the volume of this room, you probably wouldn't use that formula, right? Because all the sides, they're all orthogonal, so we just do length times width times height. But if it's not rectangular box, then that length times width times height goes out the window, and we need something else. So this would be able to get it for us. All right? I won't do that. I give you three vectors, so let's talk through how we would do it. How would I find the volume of this parallelepiped? Cross product of any two, right? So may as well just get these two, cross them, and then dot with that, and then magnitude, we're done. So your other bonus question on the take-home was to find the volume of this solid, right? So all you would have had to have done is created three vectors for each of the sides and then done the triple product, and you would have had the volume. Anyone do that one? Huh? Yeah. You may have still got the volume. It may have worked out, but you see that this formula would have been very easy to apply to that. Yeah. All right, here's one application of cross products. Torque. Have y'all heard the term torque before? Okay. If we tighten a bolt by applying a force to a wrench, then we produce a turning effect. Torque is a vector which represents the tendency of the bolt to turn. Torque is defined this way. Torque is equal to the cross product of R and F, where R is the position vector of the rigid body, the wrench, and then F is the force being applied to the wrench. The direction of the torque vector is determined by the right-hand rule. So we have the right-hand rule. If right-hand rule says that your fingers, if they curl this way, the thumb is the positive direction, right? So think about when you go and you turn a bolt, a standard bolt, all right? When you turn a standard bolt, you turn it clockwise, right? So imagine the curling this way, and it actually wants to go in, doesn't it? We call those right hand threads. Right hand threads are that way. They follow the right hand rule. Turn right, they tighten. Righty tighty, lefty loosey, right? So that's following the right hand rule. So that's the way torque is done also. Is that when you cross R and F, I'm going to show you the picture. It'll either go in or out depending on the way your F is positioned. Now, of course, if you change to left-hand threads, it throws everything off, right? What things are left-hand threaded? On bicycles, like pedal bicycles, one of the pedals is left-hand threaded. Which one? Which one do you think it is? The bottom bracket's left threaded too? Yeah.
That way when
Yeah. That's right. That's right. One piece what?
Like the driver that goes inside the hub.
Okay.
The left side. That way when it's
Then it's turning, it doesn't want to loosen it up. So there's value in left-hand threads. They're not. The worst thing is when you're trying to loosen something and you don't know it's a left-hand thread, right? And you strip the whole damn thing out. Anyone done that before? Yeah, I mean that's the worst case scenario. Yep. Okay, so what I have is I have a picture here where we can visualize the torque with this cross product. And so I have a two-dimensional picture and I have a three-dimensional picture. So the two-dimensional picture is, imagine like there's actually a bolt on the wall right here, and I've got this black wrench right here, and I'm going to grab it and I'm going to pull it with a force. How hard I pull is represented by the length of that red, okay? Then in three-dimensional space, it's hard to see it. We're looking down this way, okay? We've got the black thing here, and then we've got the red one here, and then if I pull red this way, right, the force is going to go into the page, or in this picture, it's going to go down, all right? So I just wanted to ask you what's going to happen when I start moving this red. So what happens if I drag this red and I start pulling that red one down this way? What should happen to this blue? It should get longer, right? More force, more torque. Shorter, less force. Less force, less torque. Okay, what if I keep my force the same, but now I rotate my force this way? What's going to happen to the torque? It's going to become less, right? So that's not the proper way to tighten a bolt, right? You don't hold the wrench and pull parallel to the bolt. Start pulling in on the wrench. You don't get any torque that way, right? Or just trying to push the wrench in. And nothing's going to happen, right? You get no torque. But what gives you the optimum torque? If you pull exactly 90 degrees. And you can see that illustrated a little better with the formula for the magnitude of the torque. This is the formula for the magnitude of the torque. Right? This is just an extension of what we saw earlier. U cross V magnitude was magnitude of U, magnitude of V sine theta. These two numbers, if we hold these two constant, right, the wrench is fixed, how long it is, and the force is fixed, then the only thing that matters is the angle I'm pulling at. The biggest sine can ever be is 1. And when does that happen? 90 degrees. So to get maximum torque, right, to get your maximum torque, you want to be pulling 90 degrees to the wrench. So as you come around, you want to keep your arm 90 degrees to the wrench and you'll get the maximum torque. Has anyone used a torque wrench before? Torque wrenches are used to tighten something to a point where you don't go too tight and strip them out. When you're pushing or pulling on a torque wrench, you're always supposed to have your hand, they usually have a line on the handle, where you're supposed to put that line right on the center of your hand where the force is, and you're always supposed to keep the force you're pushing with perpendicular to the torque wrench. Because if you come in at an angle like this, and push down, you're not getting as much torque, right? It's different than if you come in straight. So this is all connected to this whole cross product idea, and I hope that that kind of makes sense that way. What happens if I go and I pull this force to the other side? I mean, I pull it over here. We're going to start loosening the bolt, right? So now the torque coming out towards us. Do you see the right-hand rule? Do you see right-hand rule? The definition of torque is R cross F. So what I would have to do to help you see R cross F here, I'm going to move F down here. Okay, there's F. If I do R cross F, I need to go so where my fingers curl from R to F. If I go R to F, my torque is coming out of the page, and that's why it looks like this. If I move that over to the other side, now my force vector is like this. Now when I do R cross F, I can't hold my hand like this. I have to turn my hand over like this, R to F, and now the torque is into the page. That's what we were saying, you know, torque follows the right-hand rule. I don't believe that's the right page. 10.4, 10.4. This is actually page 564. I'm not going to give you anything as a take-home quiz today because we only met once this week. I would anticipate your next take-home quiz. I'll give it to you on Monday. Okay. Things are going to pick up. Things are going to speed up pretty quick here now. Because now we've gotten the fundamentals of vectors down. We're going to get into lines and planes and quadratic surfaces, and it's going to start coming really, really, really fast. The concepts are going to be a lot different. So just be prepared for that. If you've seen a lot of this and you've just been sitting here going, okay, it should start getting new pretty soon for you. All right? Guess that's it, right? We have a good weekend? Unless y'all want to hang out and take a quiz? No? For extra credit? No, I think we're good. I don't want to grade anything else. I've got enough to grade right now. Yeah, we should probably do that, huh? Hey, did I announce to you all about my office hours? I sent an email to everyone. Check your email because my office hours, you can now schedule 30-minute one-on-one sessions with me. And I've already had students come in. I encourage you to do that. Okay? All right, real quick, we will start out. I already know that a lot of these students aren't here anymore. So Allie's here. Patrick Daniel is here. Josh is here. Both Joshes, right? And Jose Rojas? Jose? Okay, got Jose's Raul. Joshua, I got you. Thomas Hernandez is here. Mark Cortez. Adrian. Jason. Bowley, yes. Diego. Angel. Joel. Christopher. Tamara. Damn it. Okay, anybody? I miss anybody? I called, yes, Jose, yes. I've got two Jose's. I called Jose Aguilar and Jose Rojas, so you're good. All right. You can turn this in, but I made an announcement at the end of at class today that if it's 2 minutes late, it's not accepted for next one. Okay.
Okay, thanks.
All right.
It is usually not my habit to be this absent.
No, I don't need it. That's right. So, the bonus and then this one here. Yep. Okay? All right. All right. Does anyone want their quiz from last time? I have it. Oh, no, I passed them out, didn't I? Let's see. Raul, Joshua Shaw. Joshua Shaw? Raul. Okay. This was that quiz from last time. Okay? Yeah, I can show you. Let me turn my video recording off.